Tony, remember when you asked me to do the analysis of Howard Johnson's work? You actually paid us here to do it. When Howard gave you the stuff down there.
Right, we went down to Blacksburg, and Brett and I and Pat went down and visited with Howard and Gladys, and Howard gave us this stuff, and then we drove it back, brought it to your lab, and yeah, we did. We asked you to perform an analysis. So I guess this is it, really.
Yes, so I'm here to give you the full report on what I think Howard was really up to and give you the full analysis on this DVD. Well, I was working on magnetic fields, and I was going to explain how these magnetic fields work and what I thought Howard Johnson was doing with his magnetic gates and things like that. So I was going to show some things here and some tuning apparatuses to look at the magnetic fields that we built in 1984, which is over here, and a couple of little motors that have been seen all over that are gates, you know, that have these permanent magnets. And you can see that when I get the gate near the scalar tuner, you can see the beam being emitted through the gate. See? We use what we term a magnetic detector, which is a little device which tells the polarity of the magnet when you get close. And that says that's a south pole. And if we look at the gate, it says these are all north poles.
When did you build the gate?
Oh, I built the gate in, well, let's see here. I built so many different things that it's hard to remember. This was done in, and this was posted on KeelingNet on February 22nd, 1997 at 5:27 p.m. And so this is the gate that you're looking at right here. And so I kind of wanted to go through these magnetic fields with the people to show them how you can make an asymmetrical permanent magnet, which means then you can make a permanent magnet motor if you understand the principles.
So you've been working with magnetics for a long time.
For about 30 years. So I get started at a normal permanent magnet, in my opinion. And I'm not saying that all the scientists will agree with this, but we know a permanent magnet is having a north pole and a south pole. And the permanent magnet, when it's charged, when the grains are oriented in a certain direction, in other words, if they're oriented in this direction, then our fields are going to be the north pole up here and the south pole down here. And what's actually going to happen is when this is charged, we're going to have field lines that come out around the magnet like this. And so basically what's happening here, I'm just going to use a double line. I'm not going to go into the orientation or the mathematics behind it. I'm just going to explain it in simple terms so everybody can understand what they have to do. These magnetic streams that come out of this magnet are little bitty magnets, like Ed Leedscallion said in his post. And one of these vectors, or one of these magnetic lines, the direction that the magnetic streams are flowing is this arrow. So it's coming out of here and it's going this direction. All right? And the other one is running against that, like this. And the same thing's occurring on this side over here. So here's the thing. If we took these lines away, manipulated this magnet, sorry for the eraser, but I couldn't find my eraser. If we looked at this magnet, we'd have an equator or something that's called a blotch wall. And depending on the size of this blotch wall is how powerful the magnet's going to be. So if this is really squished together in a really tiny line right here, then we're going to have a big magnetic field. So basically what happens is the energy comes in after it's charged and enters the blotch wall. And the little spirals here are the energy coming in. And so then when this stays, once it's charged and everything's oriented, it stays in a permanent magnet condition, and that means it's a permanent magnet with the north and the south pole like this. So what can we do with this magnet? We can vary this blotch wall and change its position in the magnet by how we charge this magnet. Okay, and then the south pole is much stronger and the north pole is much weaker. So now we've just altered that magnet and we've made the field from this magnet sort of go like this. See? Which gives us a strong pole here and a weak pole here.
Just by moving the blotch wall up.
Just by moving the blotch wall off in how we can charge this and change the magnetic domains in the magnet, which are these little magnets that are going to line up. So if we move this up, we have a much weaker magnet on this side and a much stronger magnet on this side, because it's going to change the way the energy input comes into the magnet. And what we're looking at is a complex theory of 4 quadrants. And I always say when I'm doing something that that's delta 0 and delta 0 and delta 0 and delta 0. So these are fields that you really don't use unless you want to accomplish something in the magnet. So if you made this blotch wall where you could manipulate this blotch wall and make it from this direction to this direction, and you modulated this blotch wall with something, in other words, with a signal, let's say, what would happen is the magnetic field would ripple on the outside, just like this. So I've been putting all this together. And so I just wanted to start out with something basic. And we have a basic permanent magnet. And so, but we have to be able to understand how you can affect this permanent magnet. If you have something that's stationary, like this, with the blotch wall that's normal, right? You have even poles. So, suppose that we just had this normal magnet, and we wanted to take this normal magnet and we wanted to increase the strength on one side. Then what we do is very simple, is we would tip this with a piece of neo iron, and now this pole is stronger than this pole.
And what would your basic magnet be? If you're tipping it with
It would be right now what you're building is an asymmetrical magnet.
Right, but before you added anything, you had a magnet there.
Right.
What's that magnet made out of?
Oh, ferrite. This is a ferrite magnet, and what we're doing with the ferrite magnet is it's easy to tip with neo.
Okay.
So we're increasing this pole with a piece of neo. on here to add strength to the magnet on that side of the field. Okay?
Okay.
So if we wanted to add strength, say, to part of the magnet, we just tip it this much and leave the magnet like this. And so our fields now are going out further than they would be. Like this. So basically, when I say this, Tony, I'm building an asymmetrical magnet.
Right.
Or something that's nonlinear.
Right.
Because it's very important to be able to do this with a magnet if you want a magnet that's going to do a certain type of work for you. So the idea was, when looking at Howard Johnson's gates, studying what Howard Johnson was doing, when Howard Johnson did a magnet, he might have a piece of ferrite right here with the north here and a south here, and he wanted to direct that field, so he might have taken another magnet and he might have cut it at an angle like this, and this would have been a south and this would have been a north, all right? And then he might have tipped this down here with a piece of neo. So what he's actually doing is he's directing it this direction. And this side of the magnet stays pretty much normal, but sort of shields it a little bit.
So the first magnet would be like ferrite, and then what would be the triangular magnet would be what? Neo?
Well, no, the triangular, these are ferrite pieces.
Okay.
Okay, but the tip
The
of
tip
it
would
is
be
neo.
Okay.
So we'll just call this neo, and this F, and this F.
Okay.
All right? So this is basically what Howard Johnson, how he was directing things around by making this. And so what happens is the field is going to go, going to sort of look like this. And so if I go over here and I get something and I look, let's say I just want to look at Howard Johnson's fields. You can see here that he's showing it. And then they've graphed out of when he makes these special magnets, that the magnetic field's light on this side and heavy on this side. And see, there's something else happening over here where the magnetic field is being sucked inward here, more or less, see it? And then he shows the magnetic lines down here of what's going on with these fields. So when you look at something that Howard Johnson did, you have to take into account that he's shaping the field that he wants. And there it is. And then this would be the contour of it, or what you would call a contour map. And this would be the magnetic lines of force as the computer plots all these points down in here. And so we can look at a few more first. And then you can see exactly what he was going to do here. If we look at it, here's some more magnetic maps. But you can see here we got completely some different shapes here. See, it's almost as if you could take this one and put it inside this one. See that?
Mirror image.
Yeah. And so if we look at his gates, when he did something, you can see here's a North Pole. And see, there's a piece of neo, and there's a cut magnetic block. And see, he says right here, notice the N, this is neo. That's a neo-south, because it's depicted as green.
And these are Howard's actual drawings.
Yes, these, and I'm going to show you a little bit more here. This can get very complicated, because when you build these gates, he knew exactly what he wanted to do and what the magnet blocks were going to look like. Of course, you know, Tony, Howard was a very secretive man, so he never really discussed any of this with just general people walking around out on the street. But,
or anybody.
Yeah, or anybody. And so when you understand how the magnetic gates work, you can do things like building trains. And let's look at something he was doing with a wheel. And you can see that nobody's even close to Howard Johnson. And this was done in 1996, because it says it right here. The twist motor using spin units. And you can see it right there for the armature. And you can see that nobody builds magnetic structures like that.
And clearly he had a method. I mean,
Yes.
this certainly wasn't random.
Yeah, so let's say we wanted to do something. See, if you look at what Howard Johnson's did, let me get this out of the way and we'll get back up to the blackboard. If you notice, see, Howard has indicated here, neo ring on rear of front car. So he's talking about a car that's moving through this gate. And you can see here very closely that the gate is ceramic, and then he's got a different type material here, and then it's rubber, and then it's ceramic, and then it's neo, N-E-O, neo, rubber. See, so what's actually happening here is Howard is making up a magnet that's asymmetrical. And what Howard can do is, if this is the North Pole and this is the South Pole, we indicate it as a switch. So what Howard could do is switch this magnetic field completely around as another magnet passed it, and this would become a South Pole, and this would become a North Pole. So this is the switch in the magnet that we've always talked about, you being able to switch the magnetic field by bringing another magnet to it, close to it, like say another pole.
Is this flipping the spin?
Yes, yes. In other words, if you were, Howard had this double spin theory, right?
Yeah.
And so what's going to happen here is when you bring this North Pole close to this pole, right? The way he's arranged the magnet by cutting all these different pieces is so these poles do a flip or a switch and then get fired out, because if it was south down here and you started to bring the magnet in,
Right.
and this thing switched, you get an energy burst that looked like this in the magnetic field. And this is actually a potential between here and here. It's a potential of magnetic energy. Normally with a coil, we put a burst of energy in it, and it's electrical energy converted to magnetic energy.
Yeah.
But see, this already has everything that it needs to do it. So if you make this magnet right, and we're getting into a little bit of that, but the point being that now I've brought this north magnet very close to this south pole, but this is very weak, and all of a sudden this is what's going to happen. This is going to switch, and this is going to become a north, and this is going to become a south, and the rotor is going to go that way. The same as the train car. So if you look very closely, he's already depicted it here. He's got it laid out to run the car through. And you notice that he's against rubber here, and the end indicates neo. You can see it here. See? Right side, rotor, and here's his layout. A ceramic neo, double rubber, ceramic neo, double rubber, ceramic neo, double rubber. See? So he's causing the switch to happen in the motor. Okay, so let's move on to a few more of the drawings, and then we'll show you what could have possibly happened with what Howard was working on. If you look very closely here, you can see what Howard's doing. You see how he's got all the magnets together? See how he's making up the gates? You got a piece of neo, you got a piece of rubber, and you can see down in this picture right down here. This is a complex network of magnets, cut magnets, to make up a switching gate. So it's not quite as easy as everybody thinks to make what Howard was working on here.
No, well, I was in his lab, and
Yeah.
you could really see the complexity of what.
Right, but if you look here, look at the complexity
Yeah.
of all this. You see, so he's making up asymmetrical magnets to drive this car through the gate, which is a standard train that people could ride on once you pushed the lever and the magnets came in contact with the gate, then the train is pulled along the track all the way to the end.
Right.
And then all you have to do is reverse the other magnet, and it's going to go backwards. Now, a way to show you that with the spins is this little motor. Okay, these are cabinet latch magnets, and this is a piece of PVC pipe.
Okay.
And you get this many magnets to fit in there. You can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let's look at this gate.
No magic to the number.
No magic
Just
to the
whatever
number,
fits.
just whatever fits. No science behind this whatsoever.
Yeah.
Anybody can do this. And what that is, what that gate looks like is like this. Okay, so now we've got our magnets in there. And we know from the magnetic indicator, because you can see this again, it says north when it lights up there. And they're all north. Now, what did I just do by putting all these magnetic north? I told the vectors on the north poles to spin. I want everybody to pay very close attention to this drawing. It's not exactly, I'm not an artist, so I'm going to get it as close as I can. I've told all those vectors to spin into the center of the gate.
So that's a Fibonacci spiral.
Yes. Yes. And on the opposite side of the gate, I told them to reverse in the center at the blotch wall and go the opposite direction. So now, here's my gate. Right?
Right.
So if I say, okay, I'm facing the gate this direction, which is this direction. Here's the arrow. You got that?
Yep.
And I'm very careful, and I come down on the south pole. See, it wants to spin in the counterclockwise direction. See?
Yep.
Okay. I let it down, and I flip the arrow over. That means I've turned this gate around.
Right.
It has to go in the other direction, which is clockwise.
Which is what the Faraday motor does when you flip the...
Yes. But this is a magnetic spin.
Right.
See, without any energy, there's no
Right.
electricity here to do that.
Right.
All right, so I can measure this gate by just taking this gate and looking at the beam. And so we can look at the gate in terms of a scalar. So when I come up, see as the magnetic materials move around, I'm just focusing the gate on it.
So this scalar detector detects any
Right.
time there's a scalar.
Right, now look at how far this is going out. See, I'm moving it, see? So now if I want to look at the south pole,
Back up a little bit. The gate, what exactly is that showing us when you
it's showing me the scalar. This is a scalar
Right.
being emitted.
and you're showing that it's
It's a
quite
beam.
You're showing it's quite far away.
It's quite focused, see it?
Right, right.
And I can flip it around and you can watch the needle jump, see?
Right.
Right, and I can show you that what's coming out of here is just magnetism, because it's not focused.
Right.
It's just a big magnetic field. So let's say I have all these magnets sitting up here. They're all opposing north poles on this magnetic motor.
Right.
Right, and I just give this magnetic motor a spin. Look at the tuner, because it's detecting the scalars. So I can actually map this field if I wanted to put this into a computer. And watch. See, it's still oscillating.
Yeah, the magnitude is sort of independent of the RPM.
Yeah.
Yeah.
And so if we go and we want to look, say we want to turn the gain down, right? Because we want to gain with this. This is a zero-sum field. This is where both signals come and are summed together to cancel out and cause a zero.
Right.
So anything that is asymmetrical to this is going to produce a wave.
Right.
If there's a differential between this one and this one. So it's a differential indicator. So if I take a wheel in space and I spin a wheel in space, here, let's back up because the fields are powerful. You can see that what you're looking at is there's a magnet out here and there's a magnet here, and you're looking at the RPM of this wheel, right, as it goes through space and causes a differential. So if I stop the wheel, it goes down. If I move the wheel faster, it generates more spatial field. And so therefore, you're going to get a higher output. And the tuner's indicating that. So if I back the tuner down, because it is a big field, you can see the needle bouncing as this rotates. And this is what it is, because it's a north and south field. Look. And that's what it's indicating right there, because if I stop the wheel, there's nothing there. Now if I go the other direction, it's going to indicate it again. Because remember, it's a continuous north and south.
And that's the Bedini coal window motor.
Yes. And any one of the motors, if I took, we're just talking about magnets. Any one of the motors, if I took any one of the motors, and anything, by the way, anything that I do in the area that has to do with magnetism is going to be detected, because that's the way I've set it up, is to be a detector.
You set the scalar
Yes, I've set the scalar tuner up now.
to detect
Yeah, and
magnetic.
you can see here, look, all I have to do is just touch. See, look, I'm not moving very much.
Hold on, hold on.
See how big that is? That means if I spin this wheel, I have to turn the gain down because the magnetic field is so great. In fact, it's beyond what the scope of the tuner is actually designed for. So we have to go backwards and then detect. So see, I want to see how it's affecting space. See? So that means it's out here. See, watch. And if I go faster, the spatial field gets warped into a bigger dimension. See, look. I mean, you got all these magnets now. And this is a spatial disturbance. See? Every time I do something, look. And if I tap on the floor, you're disturbing space. You're disturbing the magnetic field lines in space. So anyway, we've seen basically that we can measure these things if we build devices that are different to capture the differentials. But the whole thing is Howard here. And why is Howard doing what he's doing here? You can see that he's creating the exact field that he wants here. Let me see if I can get some better pictures. Here's a train going through a gate. See, Howard always puts red and green. So that means that this south here, and you can see, is going to go into that south. And see, look, he's got a tension scale on it. So he can tell you what the power is
Yeah.
as it goes through to the gate. Again, it says right here, 13 gates, 1 short, 12 normal, spare 1/2. See? And he tells you, July 26, 1994, experiment with it,
Yeah.
of this type gate. And here's experiment 46, July 25th, 1994. And every one of these is marked as an experiment to understand what these nonlinear asymmetrical magnets are going to do. And so when you put something through the gate, right, you see it's attracted in here. Watch. See? But it wants to be, I can't quite hold it because it's powerful when it wants to go through there.
Right.
But when it pushes through that gate, it's expelled.
Right.
See?
Right.
That's the switch right there.
Right.
So if I turn it around,
So you made a gate with just simple.
see, look at how it's sucked it in.
Yeah.
Watch. Kind of neat, huh?
Yeah. And the ball bearing's nothing special.
Nothing. It's a piece of iron. In fact, it helps being sucked in
Right.
this direction. It's attracted and then switched. Here it is.
Yeah.
See? And I can just take it. See? If I hold it straight. But the gate actually wants to attract in.
Whoa.
See it go through there?
Yeah.
And so we can look at the spins by just watching what the gate's doing. See, if we turn over, is going the other direction.
And just to
And it really wants to go.
yeah, oh wow.
Yeah, so,
And just to reiterate, this
that's just lines.
these are just lines,
Yes.
and this is just a regular magnet. This is not
Yeah,
a whole.
well-
These are not segments of a magnet. This is
Oh,
just
no, this is a
Yeah.
regular magnet, because I'll do this in front of you.
Yeah. No,
Yeah.
just for so people understand.
Yeah, well, I want people to understand that normal magnets, here it is. You see, I know this is the north gate, so I know I have to pick it up,
Right.
right? And so I know I need a south. That's a north, which means it's repelling that
Right.
gate, and actually is going to suck through, see?
Right.
So I need a south. So I need to put this on the north side. And that's the same magnet that's right there. And I need to just put that ball there. And it's going to do identically the same thing.
Yep. Yep.
So I can see what direction, how this gate that I built in 97 actually works. And it's a vortex. It's coming, it's sucking this direction and outputting that direction.
Is this in the magnetics textbooks?
No. No. The next thing that's not in the magnetic textbook is this. North Pole, South Pole. Right? North Pole, South Pole.
Right.
Well, everybody's been taught that those poles repel each other. So what you do is you do exactly like I showed in 97, pushing the two north poles together. And the south pole becomes weak then on each side, and the output doubles on the north side. So I'm going to just blow it up a little bit. I have a north pole here, and a north pole here, south pole here, south pole there. So assuming these are both the same size, which I did not draw the same size, we're gonna call them equal.
Okay.
These two magnets become equal, all right?
Mm-hmm.
So, yeah, I'm going to show you something. I'm going to show everybody this one time. I'm going to show you the poles. Here's the north pole. So I'm going to mark it north. So we know the other one's the south pole. What can this magnet pick up? Can it pick up this ball? No. But when I force the next north pole to this one, change it 90 degrees, how much more power is there?
Can you turn it towards the camera more? It's like a sandwich. Yeah. Okay.
Yeah. See, but alone, the south pole now has no power.
Yeah.
Because what I told this magnet to do, well, it's fun to play with magnets, Tony, because no matter what you do, they're all over the place. What I told this magnet to do was this: squish these out in a beam like this. And this to become weak. So now my fields start to look like this. And the the same for this side. That's why I developed the monopole engine, because if I have a north here, and a north here, and a north here, and a north here, right? Then I'm telling it to do this. I'm telling it to do this kind of field. Because these are souths, right? Mm-hmm. And so these are going to go directly to the shaft, like this.
Isn't that the diagram you put on your website?
Yes,
Yeah.
that's the monopole engine.
Okay.
Okay, so if I want to change the spike, in other words, if I wanted to take the monopole, which uses a coil here to trigger, what I would do is if I didn't like the normal wide beam, right? Because if you look very closely to what I just did, I've narrowed the beam. See, look, watch.
Yeah. Right.
I've told it to narrow that beam and double in power. So therefore, when I come across this coil, I come across this coil with this really sharp beam. Well, if I have this real sharp beam that just goes across the coil, I can't burn very much energy.
Right.
But I have 4 times the strength to push the monopole.
Yeah.
And it's all done through canceling out 2 poles, the 2 south poles. So, back to Howard. I think what, I want to show you some more things with Howard before I actually show a demonstration of how his gates actually look, because nobody's ever really been able to run a magnetic detector, Tony, across his gates. And we're going to do that.
Okay.
You can see they're testing this gate right here. And see, look, this is a rotary gate. See, it's got to go through a window. Notice that? Isn't this a window here? See?
Oh.
This is going through a window.
Where's the window on the Bedini cold window?
Right here, this is the window. See, you're
Oh, okay.
going
Yeah,
through
yeah.
this window,
Yeah.
right? In other
So
words,
we got a window going on here.
yeah, you got a window going on with this motor. And you can see he's building the gates for that motor down here,
Where is he building the gates?
right here.
Right there. Yeah.
See?
Yeah.
And there is how he's already figured out the magnetic fields.
Yeah.
All right, so basically, this is pretty hard for somebody to do, isn't it?
Yeah.
If you don't understand what's going on. We have to look at what Howard Johnson was really doing here. See? With the gates. See?
Yeah.
Notice the difference? See, they're offset.
Yeah.
Okay, this is what would be termed as sort of a V-gate engine that Howard was working on. Whether he completed that or not is not known. But let's look at some of the fields that he looked at. I mean, who would make magnets that look like this unless you were trying to build some kind of engine device?
Yeah.
Okay. So how do we do it, right? If you look at all these magnetic fields that Howard had analyzed here by computer, each one of these has a specific field, the north and south side. See this one spiraling around?
Yeah.
Is a completely different gate. Each one of these is a gate, and take a look at this one. Sort of looks like a top.
Looks like a jellyfish.
Yeah, with south field emanating lines there, see?
Looks like a Walter Russell
Right.
drawing.
Yes, exactly. So, and look at this one down here. I mean, if Howard Johnson knew his magnetic structures and he knew how to do it. And so let's continue on here. Let's look at what Howard was really making here.
Our most tested design.
Yes. Now here's a packed stator neo armature motor. See it? And notice the gate, it's going through a window, like the window motor right here. See how these magnets go through the window? Just this little bitty window.
Yeah.
Well, this one takes energy, but this one doesn't take any energy. And here it is. And then notice Howard here. I think this is Howard.
That's Howard, yeah.
And notice he's working on the plastic rotor to go through the gates. So he's definitely planning right here to build a rotary motor. And so if we look at this, notice this wheel. And then we look at this wheel, see he's already got it cut out for the gates. And he actually had this all put together like this. It's
kind of
we're gonna restore it.
Yeah.
For Howard, but notice the layout here as this goes around. See, these are all making V's. See them? And they're offset. Notice that? Mm-hmm. And so this type motor, if it actually ran, which I do believe that Howard would have got this to run, would actually have went until it got up to its rotational speed for the magnets.
Yeah.
And so, what are we talking about? We're talking about Howard's non-symmetrical, asymmetrical magnets. And the way Howard Johnson did this is if he had a magnet, and this was the North Pole and this was the South Pole, he would do something to make this magnetic field that normally looks like this with iron filings. And I'm going to keep this on a very simple wavelength for everybody so they understand. In other words, if you go back and you understand what's going on in the permanent magnet, you know that the permanent magnet, people have talked about the blotch wall. That's the center of this magnet. I get so many questions. John, what are you talking about? This is the blotch wall.
Yeah, you've covered that in about 3 DVDs now.
Okay.
Yeah.
So I want everybody to understand.
I just have a quick question
Yeah.
on the blotch wall. Is that in the textbooks as well?
Yes.
Yeah.
Yes. But it's not explained. It's the absence
Right.
of all magnetism.
Right.
See? Now some say that this one little arrow, we'll just call it a vector. We'll call it a magnetic stream. Let's call it a magnetic stream because that's what it is. But there's something very interesting here. The field that's being generated by this magnet is not really part of this magnet. It's part of space.
Right.
And so some people say, well, that doesn't do that. That goes like this.
It's impressing this field in space.
Right.
Yeah.
And it switches over here in the center of the blotch wall. Well, if these are all equal, and we take all this out, and I'm just going to redraw this. We'll keep the blotch wall there because we want to keep that right in front of you. The reason that it doesn't go in here, Tony, is because it doesn't have to. It's because Ed Leedscallion was absolutely right when he said this magnetic stream is spinning this direction and that magnetic stream is spinning that direction.
That was the guy in Florida that built
The Coral Castle.
the Coral Castle.
Right. And so these are neutraled out. This is just a device. This magnet now that I'm holding in my hand, right, is just a static device. It's not doing anything out there in space, except emanating its magnetic streams, which you cannot see.
Right.
But you can see them when I come close to this tuner, see it?
Yeah.
See as I turn it? Because I'm making space do this.
Right.
You see, I'm modulating space with this right now. See? And when I do that, when I flip that magnetic field, I'm actually modulating space. I'm going from north to south to north to south. And I can put this wave out in space, but it's invisible. Nobody can see this wave. But the real thing here about Howard Johnson is Howard Johnson wanted this magnet to be switchable. In other words, if somebody put a little switch in here that took this North Pole and put it this way, and this South Pole and put it this way, with a trigger. In other words, I'm going to throw this switch, which is not an electrical switch. It has to do with magnetism, the unseen force. And I come by and I do something with this magnet out here, right? And as I get close to what Howard was building here, these things can switch. Well, you can't have a permanent magnet motor unless something is switched. You have to have an imbalance in the permanent magnet motor with the rotor. So you have a coil on this side and you have a coil on this side, right?
Right.
And then when this thing turns around and gets the electricity, it repels this one. So that means there's an imbalance now and attracts the other one.
Right.
So there has to be an imbalance somewhere for that to work. So the point being that I can make a magnetic field do anything I want because a magnetic field is a complex device that I know all these streams are emanating from the magnetic field. Now, we know that this is a static magnet. It's just sitting here like this, right? And we take that magnet and we say, gee, how can we make this magnet so the North Pole is not so strong, but the South Pole's real strong. So I want to come in on this side, and I want the magnet to make a switch, and then I want it to push out the other side. Well, there's one way to do that. We can align these magnets into what I call a gate. So we would be looking at this gate. And all these poles would be the same here. Now I come through the gate, I put a little piece of steel ball here to make the magnet non-linear. I want to suck the field lines to that ball so that this looks like a south, see, to the north. And this is what you get.
So you're tricking the gate.
Yes, and then when I get to a certain point, then it's pushed, see?
Yeah.
So I want to switch this. This is an example. There's a lot of work to be done with this to make it do so that it doesn't fight going through the gate, right? But if you look at it, all these things are pushing. See? And the South Pole's out here, right? Being that they're south, their magnetic field wants to go like this, which it can't do, because it has to come in and then be pushed this way like this. See, and it can't do it here. So a little bit gets around here, and the rest gets pushed out in a scalar out like this. See? So if we map all these magnetic fields, that's what we're going to see. We're going to see what Howard's depicting right here. Something, say, like this. Or something like this.
And these are all the plots that he did at the university.
Yes, these are the plot universities. Okay, so what this allows us to do then is to build reality the way we want it by just doing this. I have this magnet and say, I want this north to be more pronounced on this side. Then I would take Howard's method and I'd put a little small neomagnet right over here, right? That had a south pole here.
Yeah.
And then what this magnetic field would do would make a lobe like this. See, it can't go that way. See, it's repelled here. So what it wants to do is it wants to squirt out like this. But this way, it wants to do this. You see what's happening here? So maybe Howard might want to trick this end. This staying the same. And putting a piece of neo here. See?
Yeah.
That's a North Pole. Which he's done in all his gates. And then this is going to make the lobe come this direction. See, and I'm going to end up with something that looks like this.
Yeah.
See? You might want it to look like that. Now that's a map that you would think would be something that the Geological Society would put out. See?
Yeah, it looks like a topographic.
Topological map, right?
Yeah.
And so, but see what's happening with these fields as he adds his magnets? Look at
Yeah.
this. See? This is telling us that Howard was going to build a motor. See, look at this magnet here. Dual banana attract. Dual banana attract. Run. Dual banana repel. Dual banana repel. Dual banana repel. Now, if you noticed in all Howard's banana magnets, he could change the influence of the magnet.
Who made these? He didn't make these banana magnets. So you could buy a
You
banana.
could get banana magnets, and they were used probably for motor magnets, around an armature.
Right. Can you still get them?
Yes. Anyway, banana magnet, he had them so they were sort of like this, because if I remember right, you said he couldn't wait to get his little rock saw out to cut the magnetic blocks for what he was going to do.
Right. He was waiting for the weather to where he could
Yes.
change to where he could get outside and start doing that stuff.
Well, if you notice, some of Howard's banana magnets right here, he's tipped with a piece of neo.
Right.
And he always indicates that with N.
Right.
And then he puts the dot here, what polarity it is.
Right.
So if this is a south or a north, then this is a south and this is a north.
Right.
This end. But this end is far stronger than that end. And that's what's depicted with what he's doing with the banana magnets here.
Yeah.
See? Asymmetrical magnet.
These are all dual banana repel.
Yeah.
Dual banana repel.
Right.
Dual banana repel. Dual banana attract. Dual banana attract. Dual banana attract.
Right. So he's changed.
Dual banana attract.
Right, but notice what he's done. If you look at his magnets here really close, you'll see he's tipped these differently.
Right.
See them?
Yeah, let me get in close here. Yeah, you can see it.
Mm-hmm.
Yeah.
Well, that's going to do something funny, because if this is the North Pole, right?
Mm-hmm.
And this is the South Pole, this is weak and this is strong.
Yeah.
So it's going to make the field uneven.
Yeah.
It's going to make the field very uneven across here.
Yeah.
See? And of course, what's going to happen here is the blotch wall is going to change position.
Yeah.
You see? Instead of being in the center where
Yeah.
it belongs, it's going to change position. Which means what he wants to have happen here is he wants this thing to move in a switch zone
Yeah.
as it goes through,
Yeah.
so that it can go through the gate, can sail through with ease. It's like adding a little piece of steel here to go into this gate.
Right.
Putting that little piece of steel like that to go into the gate. And see, it's actually floating if you look at it. If you get down below the camera, look here. See, I'm pushing.
Right. And you.
It's actually hovering. See, if I turn the gate around,
Yeah.
it's sucking down to the table.
Okay, go back to the other way then.
Yeah.
So basically, it's just hovering there.
Yeah, well,
But you have to support it.
I have to support it because it wants to flip to the side because of the spin.
Right.
But it's hovering there. See?
Right.
You can see that. And if I turn the gate the other way, that means the spin's going to go the other direction, right?
Mm-hmm.
See? And it's going to